Good afternoon all. Today we will start with the BSc second semester 3rd paper 5 of organic chemistry, in which we will see the unit number 5, stereochemistry. In the stereochemistry, as we have already learned at BSc 1 in BC 201, the basic concept of stereochemistry, in that regard we have already explained the basic part of stereochemistry. As we know that stereochemistry, it is a branch of chemistry which deals with the study of structure and properties of the molecule on the basis of 3-dimensional, called as stereochemistry, and the compounds which having the same molecular formula as well as structure formula but different arrangement of the atoms in 3-dimension or space, it is called stereoisomer, and that phenomenon is called stereoisomerism. As we know that there are two types of stereoisomerisms are there: conformational stereoisomerism and configurational stereoisomerism. In the BSc 1 we have already seen the configurational stereoisomerism, but for sake of understanding we are just going through this part quickly. So in the conformational stereoisomerism, it is a stereoisomerism in which the isomers can be interconverted into one form to other form across carbon-carbon single bond, and in that we have seen the example like conformation of alkane and cycloalkane. In this we will take one simple example, that is this is a 3-dimensional structure of simple ethane molecule, in which we have seen the orbital of covalent bond and that having 3 different substituents or 3 different groups, they are attached to the 2 carbon atoms of ethane molecule. Now, the configurational stereoisomers are nothing but the stereoisomers that cannot be interconverted from one form to other form. And if we try to interconvert such kind of bond, the molecule is break or that bond is break. So bond breaking and making takes place in the configurational stereoisomerism, and they are further subdivided into 2 parts, that is optical stereoisomerism and geometrical stereoisomerism. In the optical stereoisomerism, we have seen that the optical activity of the molecules we have observed, which based on the chiral center of the molecule, and there is a rotation of plane polarized light. So on the basis of plane polarized light, the optical activity of the molecule has been changed, and that is observed by using the polarimeter instrument. Then the geometrical isomerism is nothing but there is a restricted rotation across carbon-carbon double bond takes place, and because of that only we have observed 2 kind of isomers, that is cis and trans. So geometrical isomerisms are nothing, they are further divided into 2 parts, that is cis and trans isomer, and on the basis of different substituents present across the carbon-carbon double bond, it is also called as E and Z isomers. Now in this year we will see in detail the conformational isomerism, and in that regard we must know that the representation of the conformation of the different molecules, how we can represent the molecule, as definition shows that the stereoisomers or stereochemistry is based upon the arrangement of atoms or group of atoms in 3-dimensional, but practically when we can try to observe the structure in 3-dimensional, it is very difficult. Small molecule we can represent in 3-dimensional, but in larger molecule is very difficult, and that's why we have to represent the molecule on paper or on board by using the 2-dimensional, and for this purpose the projection formulae have been started. So on the basis of the formal 2-dimensional representation of 3-dimensional molecule, the structure can be obtained because of the projection formula. And here there are 4 different types of representation of the open chain structure, that is alkane, based on the 3-dimension and the chemical properties of that particular compound, that can be explained by using the different projection formulae. So the projection formula is very easy to understand the structure in 2-dimensional as well as on paper. So there are broadly 4 different types of conformations are there. First is dotted line wedge formula, second is Sawhorse projection formula, third is Newmann projection formula, and fourth is Fischer projection formula. So we will see one by one in detail. So the first is dotted line wedge formula. Here the dotted line wedge projection formula is generally explained on the basis of molecule which containing chiral center. As we know that the chiral carbon having 4 different groups, as we have represent this structure on the basis of a ball and stick model, here we can observe this is the ball and stick model, that we can represent the carbon which having a 4 different groups that are represented by 4 different sticks color, that is red color, white color, yellow color and green color. So on the basis of 4 different groups, when they are attached to the carbon, we can call it as chiral carbon, and that center is called as chiral center. So in this case it is called as wedge formula, and wedge and H, like dotted and wedge formula, it is also called as wedge and H, as well as dash and corresponding wedge and flying and wedge formula. So what is meant by wedge? So wedge is nothing but the bond which is nearer to the observer, nearer to the viewer, or which is above the plane. It is called wedge, that is thick line. And dotted or H line is nothing but the atoms or group of atoms which are behind the plane, or they are away from the observer. So here how we can represent such kind of projection formula? For this purpose we have to take that the bonds which are lie in a one plane, they are represented by a normal line. So like normal covalent bond, we can represent it by a simple drawing a line, that is a normal line, while the bonds or atoms that are towards us, or they are towards observer or towards you, that are represented by a thick line, or we can call it as wedge line. On the contrary, the bonds which are going away from observer, or they are behind the plane, are represented by a dotted line or H line. So it is represented by the dotted line. So here, as we know that in 3-dimensional, this is just we have seen, this is the chiral center, that is 1 bromo 2 chloroethane, if we can say that molecule, the chlorine and bromine. So in this case the chlorine and bromine that are actually represented, they are in a one plane. This is the chlorine and bromine. So here this chlorine and bromine, they are represented by a normal line, while the dotted line is represented the hydrogen atom which is going behind the plane, while the methyl group which is towards you, that is represented by a thick line or wedge line. Suppose here we can take a 2 simple molecule like ethane and butane. Everyone know that ethane having the formula C2H6. Here 2 methyl groups are attached to the covalent bond. If we can see, this is the view of observer, this is the view of observer. In this case they can be represented by a ball and stick model. There are 3 hydrogen atoms are there. So these are the 3 hydrogen atoms, in that can be represented over here, and these are representation by using the dotted line wedge formula, in which the 2 hydrogen atoms which are in a plane, they are represented by a normal line, while the 2 hydrogen atoms which are going behind the plane, they are represented by a corresponding dotted line. The 2 hydrogen atoms which are coming towards you, that are represented by a thick line. So here if we see how they can be look like in a ball and stick model. So for sake of understanding, if you observe, this is the white color bond is the central carbon-carbon bond that we have hold. The 2 hydrogen atoms which are in a plane of this carbon-carbon bond is represented by a 2 red color stick. So that is nothing but there are 2 hydrogen atoms are there, and these 2 hydrogen atoms and this carbon-carbon bond, they are in a one plane, so they are represented by a normal line. While this green colored 2 hydrogen atoms which are towards you or towards observer, they are represented by a thick line or wedge line, while the 2 remaining hydrogen atoms of the carbon which are going behind the plane or they are away from the observer, they are represented by a yellow stick. So that is nothing but when we can view from your side, then these two hydrogen atoms are towards you, so they are represented by thick line. These two hydrogens are in a plane, so they are represented by normal line, while these two hydrogen atoms are away from you, so they are represented by a dotted line. When we can just see how the another molecule, that is butane, is there. So we know that when two hydrogen atoms of the ethane is replaced by methyl group, we can call it as butane. So here if you observe, these are the three-dimensional structure of butane. This is CH3, CH2, CH2, CH3. So in this case, if you observe, when we can rotate this molecule across carbon-carbon single bond, that is the conformational isomer, then we have observed, for simplicity, just we have represent over here. Okay. So if you observe in this case, how that look like? So very simple. In this case, one methyl group is towards you, so it is always represented by which line? It is represented by thick line. This hydrogen atom is also towards you, so it is represented by a thick line. While this hydrogen atom and this hydrogen atom, they are in a plane of central carbon-carbon bond, so they are represented by a normal line. While one methyl group is going away from observer, now it is represented by dotted line, and one hydrogen atom of this carbon number 2 is represented by dotted line. So in this way, as there is a free rotation across carbon-carbon bond is there, so we can represent to rotate the molecule in different way. So that is nothing but, in this case, when we can try to represent the molecule by using dotted line wedge formula, it can be represented by normal line, wedge line and thick line. So it is called as dotted line wedge formula. Now we can see the next one, that is the Sawhorse projection formula. So in this case, the central carbon-carbon bond that is oriented diagonally backward. So that is nothing but, in this case, the central carbon-carbon bond which is in a slightly inclined position, or it is going backward. So that is in the inclined position of the plane. The front carbon atom, this is the front carbon atom, it is shown lower left hand side, that is towards you. So as far as your from your view is there, from the viewer side, this is the left hand side, while this is the right hand side, upper. So the front carbon atom is towards the lower side of the left hand, while the rear carbon atom, which is away from the observer, which is shown as a upper right hand side, so which is away from the observer, while the remaining three bonds of rear carbon atom, that is rear carbon atom as well as front carbon atom, they are represented by a straight line up to this carbon, and they having the bond angle between this is 120 degree. So in this way, in a Sawhorse projection formula, we will represent the carbon-carbon central bond in a slightly inclined position or diagonally backward direction. The front carbon atom is left hand lower, rear carbon atom is right hand upper, so this is look like a Sawhorse. So it is called a Sawhorse projection formula, while the remaining three bonds for both front carbon as well as rear carbon atom, they are bonded to in a straight line with 120 degree angle to each other. So if we see a simple molecule like ethane, if you observe in this case, in ethane, this is the central carbon-carbon bond is there. These are the three hydrogen atoms, that is the front carbon atom, this is rear carbon atom from viewer or from your side. So in this way, we can represent this molecule by Sawhorse projection formula. Okay, now same example like in the previous case, we have taken dotted line wedge formula, that is we will take as a butane. So if you observe in this case, in butane, again we have observed the same thing is there. This is the one of the hydrogen atom of the ethane is replaced by methyl group for central carbon atom. Now we can observe CH3, CH2, CH2, CH3. So in this case, in N-butane, when we can observe, this is the diagonally backward, this is front carbon atom, this is rear carbon atom. Front carbon atom have methyl group which is in a plane, and these two hydrogen atoms are towards you, that is from viewer side, and these two hydrogen atoms are away from you, that is away from viewer side, so they are in a behind the plane. while these two methyl group are in a plane. So in this way, in Sawhorse projection formula also, we can represent the three-dimensional molecule of butane in a simple way on paper and on board. So this is the three-dimensional, and on paper or on board we have represented by a single line, and that is look like a seesaw. So it is a Sawhorse projection formula. Now we will see the third one, that is the Newmann projection formula. So in the Newmann projection formula, when we see it is a planar form of Sawhorse projection formula, and in this case now we have to take the central carbon-carbon bond which is perpendicular to the plane. So that is nothing but in three dimension, whatever the central carbon-carbon bond is there, we can on paper or on board we can take as a perpendicular to that plane. So we will view the molecule from this carbon-carbon bond axis, and if you view from this carbon-carbon bond axis from your side, then we can observe front carbon atom and rear carbon atom, they are in a one plane, in one line. Just we can observe only one. So here the carbon which is nearer to the viewer is called it as front carbon atom, and this front carbon atom is represented by a circle dot, while the atoms or group of atoms which are attached directly, they are represented by a straight line, and they can make angle 120 degree to one another, while other carbon atom which is rear carbon atom which is exactly behind the front carbon atom, actually it is not look like to you because we have observed this carbon-carbon bond axis. So you can observe only this carbon and exactly it is behind. So how we can represent that one in two-dimensional? Then this rear carbon atom is representing by drawing a circle. So front carbon atom we are represented by circle dot, and rear carbon atom is represented by a circle, and the three atoms or bonds which of rear carbon atom, they are drawn up to the periphery of the circle, or they are edge of the circle, and they can make angle 120 degree to one another. Now we can look how they can be exactly observed. So here first we can see it is a planar form of corresponding Sawhorse projection formula, and in this case the front carbon atom is represented by a circle dot while or circle point, and these three hydrogen atoms, they are attached to the central carbon atom, and here we can get an angle of 120 degree. Now this is front carbon atom, while the rear carbon atom which is observed over here, this rear carbon atom is represented by a circle, and they can form a three hydrogen atoms, they can attach to the edge of the circle, while in this case this is the rear carbon atom. And when we can superimpose this front carbon atom on rear carbon atom, then we have observed this front carbon atom, they can overlap or they can superimpose on the rear carbon atom, and they can observe eclipse conformation. So that is nothing but the front carbon atom is represented by a circle point or dot, while this circle represent the rear carbon atom. So in this way, by using the Newmann projection formula, we can represent the molecule on paper or on board by a simple representing the front carbon by a circle dot or circle point, while the rear carbon atom is represented by a corresponding circle. Now when we can rotate the rear carbon atom, then what will happen? Again we have observed one more conformation that is represented in the Newmann projection formula. It is called staggered conformation. So what will happen when we can rotate? Now if you observe, this is the central carbon-carbon bond axis, you can observe from this your viewer or from your side, then we can rotate the rear carbon atom. We can fix the front carbon atom, we can rotate the rear carbon atom through 60 degree. Then what will happen? If you observe from your point of view, then the front carbon atom is circle dot or circle point. These are the three hydrogen atom. Then the rear carbon atom is represented by a circle, and the atoms or three hydrogen atoms, they are attached at the edge of the circle. So in this way we have observed in the staggered form they are away from each other, while in eclipse they are maximum close to each other. So this is the example of Newmann projection formula. Now as we have introduced a new term like eclipse and staggered. So now we will focus on what is meant by eclipse and staggered conformation after taking the example of N-butane. So similar to the ethane, when the two hydrogen atoms are replaced by methyl group, again we have observed the N-butane molecule. So if you observe in this case, it is a planar form of Sawhorse projection formula. So from your point of view, when we can observe, this is a central carbon-carbon, that is carbon number 2 and carbon number 3. So this is carbon number 1, this is carbon number 2 and carbon number 3. So from your point of view or from viewer side, this is the central carbon-carbon atom which is perpendicular to the plane. And from view, when we can observe, this is the front carbon atom, this is rear carbon atom, and front carbon atom having one methyl group and two hydrogen, while rear carbon atom also having one methyl group and two hydrogen. So they are exactly behind to one another, so they can be look like eclipsed conformation. And when we can rotate, similar to ethane, that we have fixed the front carbon atom and rotate the rear carbon atom through 60 degree or by different rotation by 120, 180, then we have observed a staggered conformation. So in this case, if you observe, this is the front carbon atom, and that can be represented over here. Again the front carbon atom, one methyl and two hydrogen atoms are there, while the rear carbon atom also having two hydrogen and one methyl, and these two methyl group are maximum away from each other, so they are most stable one. So this is a staggered conformation. So here we can represent the molecule in this way. Now, so by keeping the front carbon atom fixed, and when we can try to rotate the rear carbon atom through different angle from 60 to 360 degree, we have observed infinite number of conformations. So on the basis of such kind of rotation, when we can observe the three basic types of conformations are there. First is eclipsed, second is staggered, and third is skew conformation. So first is eclipse, second is staggered, and third is skew conformation. So we will see one by one. Now, so what is by eclipse conformation? As the conformation about the carbon-carbon single bond in which the atom or group of atom are attached to the front carbon atom as well as rear carbon atom, they are maximum close to each other. So in the ethane molecule, when we can see such kind of molecule is here, then we can observe from your point of view in Newmann Projection formula, this is the front carbon atom, this is rear carbon atom. In eclipse conformation, the front carbon atom groups and rear carbon atom groups are maximum close to each other, and they can be come exactly behind to one another. From your point of view, when we can observe, both red color hydrogen atoms are exactly behind to one another, and it occur at dihedral angle 0 degree, 120 degree, 240 degree and 360 degree. So that is nothing. When we can measure the dihedral angle, then this dihedral angle is 0 degree. When we can rotate this to 120 degree further, then you can observe again they are maximum close with respect to the dihedral angle, and this is called as eclipse conformation. While in staggered conformation, the front carbon atom and rear carbon atom groups, when they are attached to one another, they are maximum away from each other. So that is nothing but, in this case, this is the eclipse form. When we can rotate this through just 60 degree, then you can observe what will happen here. If you observe from your point of view, this is in a one plane, this red color hydrogen and this red color hydrogen of a rear carbon atom and front carbon atom, they having a bond angle 60 degree, that is dihedral angle. So here the atoms or group of front carbon atom and rear carbon atom, they are maximum apart in a staggered conformation, and it occur in a dihedral angle 60 degree, 180 degree and 300 degree. So that is nothing but with respect to the front carbon atom hydrogen, rear carbon atom hydrogen, now the red color, if you observe, they are having the dihedral angle 60 degree. So that is nothing but they are maximum away. So when we can rotate this, as we know that it is a conformational isomer, there is rotation of or interconversion across carbon-carbon single bond takes place. We can rotate and we can observe a number of different isomers. Okay, so this is the staggered conformation. Now this is the exact structure of staggered conformation. That is nothing but these two hydrogen atoms, they are maximum away, that is 180 degree when we can observe this bond angle, and when we can rotate further, then we can observe this is 240, and when we can rotate this, we have observed this is the 300, and in this case when we can observe this front carbon atom hydrogen, and this is now we can rotate through 300 degree and they are away from each other. So in this way we can represent the staggered conformation. Now we can see the third one, that is the skew conformation. So what is a skew conformation? It is an infinite number of conformation that are formed between the dihedral angle 0 to 360 other than eclipse form and staggered form. So that is nothing but those dihedral angle other than eclipse and staggered, that is 0, 60, 120, 180, 240, 300 and 360. Other than this, apart from this dihedral angle, whatever the angle we have observed, we can get a different conformation, and that is called as skew conformation. So when we can represent our stability concern, that in the next part we will see in detail. So just we can see that is a skew conformation. How it will look like? So if you observe the eclipse form, in the eclipse conformation, this is the eclipse conformation, in which we have observed the front carbon atom and rear carbon atom, they are exactly behind to one another. When we can rotate here in a staggered form, then we have observed this is 60 degree, they are away from each other. When we can try to rotate further, or this is staggered form, previous one is eclipse form, in between these two, that is 0 to 60 degree, whatever conformation we can observe, suppose we can say that this is 0, just we can rotate here. So if you observe, this is the bond angle around about 20 degree. So that is nothing but in a 20 or 0 to 60, whatever the conformation we can observe by rotating the rear carbon atom, we have observed the number of conformation, it is called skew conformation. So in this way we can observe the skew conformation. Now before we can see in detail the next part, as we have going through one new term, that is dihedral angle. Up till now we have observed the simple angle when the two bonds are attached, and we can observe the angle, that is a normal angle. Here we have seen a new term, that is dihedral angle. So we can observe what is meant by dihedral angle. So dihedral angle, here the angle which is created by two intrinsic planes. So plane is nothing but in this case when we can observe the bond angle between the front carbon atom hydrogen, front carbon atom carbon, and rear carbon atom. So this is one plane, and second plane is the rear carbon atom hydrogen, rear carbon atom and front carbon atom. So these two planes, intrinsic planes, they can form an angle, it is called as dihedral angle, which is represented by theta. So here we can rotate the rear carbon atom either clockwise or anti-clockwise. In both the cases we can observe the dihedral angle, and here it can be represented by simple, if you observe the plane for this, suppose we have observed this front carbon atom hydrogen and this is rear carbon atom hydrogen. In this case we have observed the dihedral angle is 0 degree. Now when we can rotate the rear carbon atom through 60 degree, then you have observed there are two different planes. Now so in this case when we can observe this one from your point of view, then this is the one plane and this is the another plane. So these two different planes are there and they can form a bond angle, that is 60 degree. It is called it as dihedral angle. So do you understand how they can be look like? So dihedral angle is represented by these two different planes and they can be easily find out. So that is represented in a PPT how they can be look like. So eclipse conformation is having a 0 degree, that having a angle of this two hydrogen atom is 0, while in this case when we can observe this is the front carbon atom hydrogen, this is rear carbon atom hydrogen, and they can be observed here as a dihedral angle 60 degree. So in this way we can represent this. Now the fourth projection formula, that is the Fischer projection formula. So in the Fischer projection formula, it is a two-dimensional representation of the molecule of three-dimensional. Here generally we can use the carbon atom which is chiral, having a chiral center, or they having a chiral carbon, so they can be made across the carbon which is having a 4 different groups. So in this case, the Fischer Projection formula is nothing but we can represent the molecule in vertical and horizontal line. Vertical and horizontal line. So that is nothing but, in this case, when we can represent the molecule in a horizontal line, that is nothing but that molecules, they are coming towards you. They are coming towards you. Now if we see, this is a simple ethane molecule. They are represented, this is the carbon-carbon central bond. This we can see in a perpendicular manner. Now this is the bond axis. In this case, when we can observe, these 2 hydrogen atoms, they are towards you. So that are front carbon atoms, hydrogen, or it is represented as a wedge or thick line, right? And these 2 hydrogen atoms are also towards you or towards viewer. These are a thick or front hydrogen. While the vertical line, now this is the vertical line. So this central carbon-carbon bond and these 2 hydrogen atoms which are represented by yellow color, they are behind the plane or they are away from the observer. They are represented by a vertical line. So in a Fischer Projection formula, we are represent the molecule in 2-dimensional by drawing a vertical line and horizontal line. So when you can draw a horizontal line, that indicate that atoms or group of atoms, they are towards you, while the atoms or group of atoms which are present on a vertical line, they are away from you. So here, when we can take a symmetric center that having 4 different groups, that is bromine, hydrogen, cyanide and amines, and this is the view of viewer, then we can observe this cyanide and NH2, they are towards you, while the carbon, bromine, they are away from you. So they are represented by a vertical line, and NH2 and CN are represented by a thick line, that is horizontal line. In this case, we can take, illustrate this point, that is the Fischer Projection formula, by taking a different example. First we are going to take the ethane molecule that just we have observed over here. This is the ethane molecule, and in this case, when we can convert this in 3D to the 2D form, that is represented by a Fischer projection, that is one vertical line and 2 horizontal lines are there. So in this case, when we can observe, this is the vertical line, these 2 hydrogen atoms are behind the plane, while these 2 hydrogen atoms are towards you. So that is nothing but these 2 hydrogen atom of 1 carbon atom, they are towards you, and this is the front carbon atom, these 2 hydrogen atoms are again towards you, while the third hydrogen atom of the front carbon as well as rear carbon atom, they are behind the plane, so they are in a vertical position. So if we take the example of propane 1,2-diol, in which carbon number 1, 2, 3 and the 2 hydrogen atoms are there, they can be represented by Fischer Projection formula in this way, that CH2OH carbon number 2 and hydrogen, they are represented, or CH3 group, they are behind the plane, so they are in a vertical position, while this is the view, or we can view from this angle, that is nothing but hydrogen and OH, these 2 groups are towards you, so they are represented on a horizontal line. So H and OH are in a horizontal line, while this CH2OH and this CH3, they are going behind the plane, so they can be represented on vertical line. So this is vertical line, this is horizontal line. Now we can take one more example, that is lactic acid, in which 4 different groups are there, that is COH, methyl, hydrogen and corresponding OH. So here, when we can represent this molecule, the COH group and CH3 groups, they are going behind the plane, so they can be represented by vertical line, while hydroxyl group and hydrogen, they are viewed towards you, so they are represented by the horizontal line. So in this way, by using the Fischer Projection formula, we can represent the molecule in 3-dimensional, and that is very important for find out the nomenclature, that is R and S system in detail on the basis of Fischer Projection formula. And that's why all these 4 projections are very, very important to represent the different isomers instead of 3-dimensional to the 2-dimensional. Mostly we can use Newmann Projection formula commonly for representation of the molecule along with Sawhorse Projection formula. Fischer Projection formula we can represent for the find out the R and S configuration, and mostly for determining the R and S system. Such kind of questions are asked in SETNET as well as the NET CSR exam commonly. So today we will stop over here, and on next lecture we will see how the conformation and conformation analysis of alkane molecule takes place, how they can give stability with different conformation by rotating the carbon-carbon single bond in detail. Thank you one and all. झालो. Después trabajamos.